As with most of the supervised learning techniques, the decision tree technique goes through a process to optimize the complexity of the model. This process is called pruning. The output of the growing phase of developing a classification tree described in the last few slides is a full tree, also called a full-grown tree or maximal tree, because it represents the maximum number of splits the split search algorithm can make in order to identify pure subsets. In a full tree, all leaf nodes are pure subsets, and it is the most complex tree you can create for the dataset. A full tree, however, tends to overfit the training data that is used to grow the tree. Therefore, it may not generalize to unseen datasets very well. As the figure at the bottom of the slide shows, when the model grows more complex, it will increasingly reduce its error rate on the training dataset. In the case of classification tree, the error rate of the full tree on the training dataset would be 0 because all leaf nodes are pure. However, when you apply the model to an unseen dataset, for example, the validation dataset, the error rate would initially decrease, but then after a certain point, the error rate would start to increase. For a full tree, this is especially true for the nodes and the branches close to the bottom of the tree, as these splits are based on a very small number of cases, therefore tend to fit the noise rather than the underlying patterns of the data. Therefore, in order to optimize the complexity of the classification tree, following the growing phase, we prune the full tree by removing splits starting from the bottom of the tree. This point can be illustrated with the example in the next couple of slides. This slide shows an example of the full tree generated from the dataset of 20 bank customers. Since the dataset is small, the full tree is not overly complex. The scattered plot on the left shows the recursive partitioning process on the dataset. As you can see, all resulting partitions are pure, which means that each partition only contains cases that belong to the same class. The full tree would have a misclassification rate of 0 on the 20 cases used to grow the tree because all leaf nodes are pure subsets. Now let's apply the full tree in this slide to an unseen dataset, the validation dataset. If you apply the full tree to the second record, where the customer is a 23-year-old male with an income of $60,000. The customer's age is less than 49. It is also less than 23.5, and the income is greater than $59,000. So the customer is predicted to respond to the home equity line of credit offer, according to the classification tree. However, the customer actually belongs to class 0, which is the class that does not respond to the offer. As you can see in this example, even though the misclassification rate of the full tree on the training dataset would be 0, when it is applied to a new dataset, the misclassification rate increased to 1 out of 5, or 20%. Now let's look at a simpler tree than the full tree in the last slide. As you can see, the classification tree only has 2 splits and 3 leaf nodes. If you look at the recursive partitioning process displayed in the scatter plot, only 3 partitions were made, and one of the partitions is not completely pure. However, if we apply this simpler classification tree to the same 5 cases in the validation dataset, you will find that the predictions are all accurate, suggesting a 0% misclassification rate. As this example demonstrates, sometimes a simpler tree would generalize to new datasets much better than a more complex tree, such as the full tree. We will prune the tree by removing the branches starting from the bottom of the tree, and we prune the tree in order to optimize the complexity of the model and improve its ability to predict new cases more accurately. By removing the splits one by one from the bottom of the full tree, the pruning process would generate a set of candidate classification trees with increasing simplicity. Performance measures such as misclassification rate of these candidate trees on the validation dataset are compared to identify the tree that produces the lowest error rate, and this tree is called the minimum error tree. The minimum error tree is the smallest or least complex tree with the best predictive performance on unseen data. So, is the minimum error tree the tree with the optimal complexity? Well, since the validation dataset is also a random sample of the entire dataset, to account for the sampling error, we can relax the misclassification error by 1 standard error and see if we can identify an even simpler tree. If we are able to find an even simpler tree that has a validation error that is within 1 standard error of the minimum validation error, then that tree is called the best pruned tree. As the best pruned tree accounts for the sampling error, and it is often smaller than the minimum error tree if it exists, it is often used as the final decision tree model. However, in many situations, you may find the best pruned tree and the minimum error tree to be the same tree due to the fact that no simpler tree that has a validation error that is within 1 standard error of the minimum error. Let's look at some R results here to get a better understanding of the difference between the best pruned tree and the minimum error tree. The R results shown here is a complexity parameter or CP table that displays 9 candidate trees with varying complexity. If you look at the N split column, it shows the number of splits in each tree. The more splits, the more complex the tree. The column X error is the cross-validation error for the tree relative to the naive rule, which classifies all cases into the predominant class. The first tree in the table here represents the naive rule, as it has no split and a relative cross-validation error of 0. As you can see from the X error column, tree number 5 with 8 splits has the lowest validation error among all the trees. Therefore, it is the minimum error tree, or the simplest tree with the lowest error rate. The last column, X standard, is standard error. So, if we add the standard error to the validation error for tree number 5, we will get 0.8971. The question is there a simpler tree that has a validation error that is less than 0.8971? Well, tree number 3 with 5 splits has an error rate of 0.8791, which is less than 0.8971. So tree number 3 is the best pruned tree, and tree number 3 should be selected as the final tree model. In some software products such as R, instead of using a separate validation dataset to prune the data, we can also use the k-fold cross-validation technique to optimize the complexity of a classification tree. I'll show you how to do this in software demonstration later. Now that you understand how classification trees work, let's work on a problem with a relatively larger dataset. So Hayden from Sunnyvale Bank has compiled a dataset on 500 customers who received home equity line of credit offers from the bank in the past, including their age, sex, income, and whether they responded to the offer or not. Hayden wants to use the dataset to develop a classification tree to predict whether a bank customer would respond to a home equity line of credit offer, and use the tree model to score the 20 new customers in the score dataset.